All right, there we go. So as I said, the topic is network structure and community detection. So we're going to talk about the ways, the structure of the network, how to analyze it, and how to find communities within the network. And we're going to define what communities are, right? So to get started, when we look at large networks, they usually have a sort of very, very typical structure, which can be defined as a core periphery structure, where there is this internal core where you have a lot of nodes connected. And then you can think about this as like sort of going in the layers, and eventually you get those nodes that are maybe lightly connected, or here on this picture they call them whiskers. And most of the networks you analyze will have this type of a structure, right? So there'll be a group of nodes that are very, very well connected. And then you'll see, sorry. And then you will have sort of other nodes spread around, okay? So the question is, well, if there is any ways to find that core structure, because those hanging chains of nodes, sometimes it's actually very useful to be able to detect them and cut them out, and then focus on the core structure of the graph. So there is a formal notion of the core, right? Core is not just you draw it. It's not just an abstract thing. It's a very well defined mathematical object. And so a core of a graph is a maximal connected subgraph where all the vertices have degree at least k. So a k core has all the vertices at least of degree k. So which means it will be vertex of degree k or less. Now, the definition by itself does not tell you a lot about what the core structure is of the graph, but it is very useful to think and to look at the algorithm that allows us to detect that core structure. So in a nutshell, the idea is that you can decompose graph into the layers, and you can think about this as sort of onion, right, with layers surrounding the kernel. And so the way to construct this k-core representation is the following. So you can think about what's called also shells, and shells are those subgraphs where the nodes of the same core number belongs to. So let me try to explain this in this constructive manner, and then we'll see if it will be clear or if we need to go further into this. So imagine that you have the graph, and then I'll ask you, okay, go find all the nodes of degree 1 and cut them out, right? So node of degree 1 are those nodes that have only one neighbor, right? So then what you're going to do is you're going to say, okay, well, no problem, right? I can go around and I can cut out those nodes. For example, I can cut out this node because of degree, like this one is the degree 1, right? This node is degree 1, so I can cut it out. I can cut out this node. I can cut out this node. I cut out this one, this one, and this one. These are the nodes of degree 1, right? But then what happens? When you cut out a node of degree 1, there might be some nodes, like this guy, that was of degree 2, but after you remove its neighbor, its degree dropped, and now it's again degree 1. So we remove it. And we do the same thing with this node. This guy is already gone, this gone, okay. This guy also dropped its degree from 2 to 1, so we remove it. Now what happens? Those nodes that are left, they all have degree 2 or greater. And so then we stop. And so what happens is this all this, internal, like this whole thing, was a core 1. It had all the nodes of degree 1 and above. The nodes that we removed right now is called shell of degree 1, and that's what we removed. And what remains inside is a core of degree 2, or 2 core. Okay? Does make some sense? Okay. And then we keep going, and that way there is this, again, there's this, the whole thing is a 1 core, then this structure is a, core 2 or 2 core, and then there is this structure that remains is a core 3. And if we start going further, it will completely dissolve, like dissipate, right? Because all the nodes there will go away if we start cutting things out. So again, the cores are those, you can think about cores as matryoshka, right? Matryoshka doll. And then, if you, on the other hand, the layers or the shells, that sort of representation or sort of onion kind of thing. Okay. Okay. So the formal definition, again, a K-core is a maximal connected subgraph which have all vertices with a degree at least K. So 1 core has everything with degree 1 or more, 2 core everything with degree 2 or more, 3 core degree 3 or more, etc. But the trick is when we try to build this, and when you remove, say, degree 1, we need to make sure that all the nodes whose degrees drop because of the removal, we also need to remove them. Okay. So that's the K-core decomposition. So decomposing graph into these layers is called K-core decomposition. And why do we want to do it? Well, because this is actually a very nice and convenient way of getting rid of sort of dangling chains. Why? Well, because think about this. If there is a chain here, like long chain, and the only thing you for example want to get rid of it, but you think that, like, look, the way to get rid of this chain is just let's remove all the nodes of degree 1. Don't do the K-core, just remove all the nodes of degree 1. Well, then it will just remove this guy, right? But then the chain still remains. But if I say, hey, look, let's remove, the nodes of core 1 level and stay only with core 2 and above, it will automatically get rid of this entire chain, and eventually it will cut at first here, there, and when we get when we're using core 2, we're going to be left only with this part. And so it's nicely get rid this K-core decomposition. If I say get rid of core 1, it will get rid of all those nodes and all those chains. Does it make sense how we can use it? Okay. This is actually a very, very powerful pre-processing technique. If you have graph with a lot of those dangling nodes, a lot of things like here in this picture, like those whiskers, and what you're really interested, and very often you are really interested in what's happening, inside, right? So then this K-core decomposition is a tool to do this. And it's also very, very efficient. So because it's actually a linear algorithm, and so you can easily, it can easily handle very large graphs, which is quite important when you use it in practice. So here's an example. This Dhaka Karate Club, and I think we looked at this graph before. This is a K-core decomposition run on the Zachary Club. And so it is color-coded by, actually not by cores, but by shells. And so this is one shell, right? So here it is, all those nodes. Actually, it's not 1, 2, 3 cores. This is, sorry, this is 1. And the yellow ones are all core 2, right? They all have shell 2, they all have degree 2. And then the green guys are shell 3, and you know, the light blue are shell 4, right? Or core 4 at the same time. So that's that. Or if we can also want to look at in more details into, say, larger graph, it's the same thing. I try to decompose things. And for example, here, when we decompose this, the one shell has 864 nodes. You just barely see it, but that's what it does. And 2 shell has, you know, 452, with 3 shell 130, et cetera, et cetera. And if you think about cores, again, core, it is, you know, the set of shells makes a core. Then, you know, that's the size of the cores. So the way to understand this picture is on the very left picture, I color coded all the cores. And when you go left to right, here we just extracted, you know, the core of degree 2. So this is a core of degree 1, so which is the entire graph, all connected graph. This is a core 1. Then we remove red nodes which form shell 1. And so what we have left is core of degree 2. So every node here has at least, you know, 2 connections. And then you remove that and you got core of degree 3. And then you can see here, this is going to be core of degree 4 and core of degree 5. Okay. So this, and you notice the nodes are getting, of course, more and more and more connected, because again, core is a subgraph that contains all the nodes of degree k and above, right? So it's going to be denser and denser and denser connected. All right. So that's the way to find, when you have a large graph, to kind of slice it slowly, right? Like actually peel out layers and get to the deep inside of the graph, see those highly connected nodes. Okay. Any questions here? All right. So again, guys, this is extremely powerful technique as a pre-processing for the graphs. When you have very large graphs, quite often those dangling nodes, they're abundant, and you might want to get rid of them, because you might be interested in, you know, deep inside the sort of the fundamental structure in there. And so to get from there to here, K-core will do the trick. Okay, so that was sort of the story of how to, you know, slice the onion, right, if you wish, peel the onion. So now here's a different part of, there is a different algorithm and a different sort of target, the different goal. If you look at this picture, you can probably notice some groups of nodes that are very well connected, right? So if you look closely, there is, of course, you can instantly, and you know, human eye is actually very good at it. We can see these guys, right? What else? What else is well connected? There is here, and at least I can see like here, right? So what I actually outlined, these are called cliques, or a complete subgraph, where every node is connected to every other node, right? So these are a group of nodes that are completely, you know, connected among themselves. there is a reason why we're noticing this by our eyes, is because, you know, the way sort of the picture shows it. The question is, can the computer detect that, right? And sort of what, you know, the formal definition. Now, if you think about this for a sec, you know, a clique, of course, depends on the size, right? So if you have 2 nodes, that's a clique because it's maximally connected subgraph. Now, if you have 3 nodes, that is not a clique, this is a clique, because that's as much as you can connect it. If you have 4 nodes, say, this is not a clique, this is not a clique, this is not a clique, this is a clique, right? And so on and so forth. So depending on how many nodes you consider, your cliques look differently, but the point is the clique is a completely connected subgraph made of those nodes, right? And when you look at this picture, there's some sort of trivial cliques, right? So pretty much if I take subgraph like this, and here's a connection, well, it's a clique, but you know, it's not an interesting clique, it's obvious clique, right? Or if I take these 3 nodes, well, this is also a clique, but it's not interesting, it's like of the size 3. And then what we see here, let's say we can take these nodes, 4 nodes. These are not cliques because these are nodes, right? These are edges. What's missing is this edge. If this edge were present, that would be a clique. But you know, it's not, so it's not a clique. But then I take those guys, say this 5, and I realize they all connected, right? So what's interesting to us is to find, you know, not these cliques that are of size 1 to 3, but we're looking for those that are like largest, right? And that's what's interesting. Now, the problem is that it's not a very trivial algorithm to find those cliques. In fact, it's, you know, pretty much, you know, you really need to go through all the possible combinations, and the best algorithm is exponentially hard, right? Now, there are some algorithms today that can do some approximate clique finding that are, you know, better than that. But it's still very challenging numerically. Plus, in real life, in reality, we can rarely meet those completely connected subgraphs. Because if that's the definition we make, and let's say this guy misses this one edge, right? According to our definition, it's not a clique anymore. But you know, when you look at it, okay, out of all the possible whatever edges is there, one is missing. So why, you know, it's still very interesting, still very, very tightly connected group of nodes. Why do we ignore it, right? So these are cliques, and those tightly connected nodes that have a very good connections, but not clique, they're usually called communities, and we're going to talk about them, you know, in a couple of minutes. But if we focus and stay with this clique definition, well, these are cliques, and it's possible to find them. It's not very easy. The algorithms are not very scalable, but if your graph is not very large, you know, you can do that. And if by whatever reason you think about, say, you know, language networks or any other networks where it is important to actually have all the nodes, you know, precisely all of them, you need all of them to be connected, you know, with each other, and you want to find those structures in the graph, well, they're called cliques, and yes, there are algorithms to find them. So here's an example of finding this maximum cliques, so the largest cliques, within the same graph, the same quadratic graph as we looked before. So here they are. There are sort of the largest cliques here of the size 5, and these are these 2 cliques shown on the left in blue and on the right in red. So these are actually, cliques. So those 5 graphs that are subgraphs, 5 nodes that are all connected. Okay. So there are algorithms. You can actually just search for cliques, maximum cliques, and the algorithm will find it. But again, the algorithms are not very efficient, so it might take a while. And in many graphs, maximum cliques will not be large or extremely interesting. But again, it sort of depends on the application you're looking for. Any question about cliques? Is it clear what clique is, right? Okay. Okay. So now we're going to switch to sort of the main topic for today's lecture, is that network communities, network community detection. And the idea is that, when you look at these graphs, and, this is an example of some sort of one of the graphs, you realize that there are some groups of nodes like here, or maybe, this one, or maybe we can think about this group, this group, this group, well, in fact, this 4 nodes, and this is a clique, by the way, right? Maybe sort of this one. So there are groups of nodes that are more connected among themselves than with the rest of the graph. And again, with our eyes, we can detect them very easily. Well, the question is, can we actually detect them automatically, right? And so there are different, again, names for this. Sometimes it's called communities, right? Sometimes people talk about clusters. You can think about, your close friends. You can look here. You can look this way for very many different sort of reasons, and all of them kind of go under the name of communities. And so the way, the finding communities or community detection is a very popular and very well studied problem with lots of approaches. And in fact, those communities, those clusters, if you wish, they can be found quite efficiently in a very large graphs. And again, examples could be, you can think about, I don't know, phone network or social network, and you want to find groups of people that are very well connected among themselves, right? Or communicate a lot among themselves. This is problem of, for example, for segmentation in marketing. There is corresponding problems in biology, et cetera, et cetera. So there are a lot of ways where it can be useful. Now, we're going to look at specific case of undirected graphs and connected graphs, connected undirected graphs. Now, the reason is, it is trivial to, of course, detect this kind of outlier, right, disconnected. So it's not interesting. And we're going to talk about undirected, again, because, here what's important is a connection, not the direction of the connection. But these algorithms, they will work as well on the directed graphs. Well, I mean, what you do is you just take and drop the direction, you make it undirected, and then you run this type of algorithms. Okay. So what makes a community, right? When we had a clique, the definition was very precise, right? It was mathematically precise. It's a group of nodes where every node is connected to every other node. Here, what we're trying to do is we're kind of trying to relax. We're trying to relax this. And relax, I mean, we want to relax this definition. And so we want to kind of have those groups of nodes that may be missing a few links, they're still interesting for us. And so we want to detect them. Okay. So what makes a community? In fact, this definition comes from social network analysis from, Westerman and Faust's book. There are a couple of things, there are a couple of properties. One of them is mutuality of ties. So, pretty much everyone in the group has edges to one another, to each other. And that really means that if we look at the connectivity, well, some of the edges might be missing, if you compare it to clique, but that's about it. compactness is the notion that you know, every node in the group is reachable from any other node, not necessarily directly, maybe in 2 steps, but it's very close. Then there is a, you know, density of edges, which is you know, high frequency of ties within the group compared to the ties to outside of the group. And it's also kind of separation. So a lot of ties inside, few ties to outside, right? Okay. But these are, you know, kind of, you know, hand-waving arguments, right? This is not a definition, so we're going to try to be a little bit more precise, though, you know, we cannot be mathematically precise here. So network communities are groups of vertices such that vertices inside the group are connected with many more edges than between groups. That's a sort of formal definition we currently have. And that's, you know, typically being used by data scientists, right, by network scientists. You notice that it is not precise in the sense, in the mathematical sense, right? So it just says, okay, community, group of nodes where more networks, where more connections within the group than you know, between groups. And so, which means there might be very many different algorithms allowing you to find those communities, and the results might not coincide. So one algorithm can, or one person can say, okay, this is my community. Another person will say that's my community. And in fact, both are correct in terms of this definition, simply because the definition is not very precise, okay? So that's something to keep in mind. Now, we're gonna be looking at what's called non-overlapping community, where each node can belong or can be assigned to only one community. So, you know, you kind of, I mean, if we're looking for, say, communities, I don't know, Democrats versus Republicans, well, you cannot belong to both of them. You're either Democrat or Republican or independent, right? So they're like sort of 3 communities in some sense of people, but you cannot belong to 2 of them. Now, this is not the only way you can actually think about overlapping communities, that there exists an entire class of algorithms for that. But right now, we're going to look only at non-overlapping communities. All right. So first of all, community density. The way to define this is sort of quite natural. If we have a graph and we have some number of nodes in there and some number of edges, what we can do is we can say, look, the density is the ratio of the edges that are present to the maximum number of edges that are possible, right? So, you know, if we take, you know, as I said, a graph like this, right, with 4 nodes, we can have 6 edges maximum, and right now 5 is present, so the density will be 5/6, right? So that's graph density, right? So we can calculate the community internal density, and that's what I just calculated here. And then you can say, okay, well, this community connected to the graph, so we can actually calculate, you know, external density of the graph itself. And then we'll say, okay, community or, you know, cluster exists if the internal density is greater than the average density for the graph, and external density is less than average density for the graph, right? So in some sense, what you're saying is, okay, well, there is some density of edges in the graph, and we're just trying to look for the spots where the density of the edges are higher. And then that spot where the higher density edges, that will be your community. I mean, this this sounds reasonable. The problem is it's actually very hard to do because this definition assumes that you understand where a community is, right? So you know where the, sort of the boundary of the community. It's sort of definition that allows you to prove that something is a community, but does not allow you to find. Because in order to use this, you need to go through all the possible combinations of nodes. For each possible combination of each number of nodes, you might try to find the density, and then you say, okay, if the density is above the average for the graph, then it's community. But the thing is, it's factorial large number combination of the nodes if you would just want to try it. And so, you know, as a method of finding communities, it's not going to work. It might work as a verification that what you found is a community. But by using the definition, you cannot find communities, again, simply because you will have to go through so many different options, combinations of the nodes to form those communities. Okay, so then what do we do? Well, there are a couple things. Before we jump into you know, those methods of finding, I also want to talk a little bit about the notion of graph cut. So graph cuts or graph cut is a partition of the vertices into two disjoint sets. Just thinking visually, it's really just taking and cutting out some edges that will separate your graph in two separate pieces. So if I look at this picture, there were the green nodes, and then, you know, there's a sort of the rest of the nodes in the graph. And I can think about this group of nodes, let's say it's forming a cluster or a community. And then there is this boundary, and the boundary goes in between nodes that belong to the community, belongs to the cluster, and do not belong to the cluster. And then graph cut means I partition it into these two groups, or thinking visually, it means, you know, I cut those edges that connect the groups. So here on this picture is going to be blue edges. So I pretty much remove those blue edges. Notice if I remove those blue edges, I separate this graph into two disjoint sets. One of them will be my community, and the second will be the rest of the graph. I assume that this is connected somewhere else, you know, to the bigger graph. Okay? And so the cut itself, the value of the cut, is calculated as just the number of edges that you need to remove. Does this make sense? So for example, if I have this kind of picture, and I have a node here, I can do this and split this in two. This will be the cut. The weight of the cut, or the value of the cut, is 1, because it took me one cut to separate this into two subgraphs. One subgraph of this node 1, and the other subgraph with 4 nodes. Okay? Or I can actually cut it here, and then I separate the graph into subgraph with 2 nodes and 3 nodes, and the weight of this cut is 3, because it took me 3, you know, I had to cut 3 edges to split this. Make sense? Okay. All right. So, why do I want to do this? Well, because I can actually use this metric cuts to evaluate the quality of separation, or to evaluate the clusters. Because remember, when we defined the cluster or the community, we said, like, look, it's a group of nodes that are better connected inside than with outside. And so to kind of evaluate the connection with the outside world, I can say, look, it takes me, you know, 10 edges to cut it out. So, 10 is how well it is connected to the rest of the graph. Having said that, you also realize that, yes, again, it's the same problem as with the previous metric, which was with the density. I need to know what to cut out. If I know what to cut out, if I know how to split them, I can calculate this metric. But the question is, how do I find what I cut out? Here I showed you that this is a cut, but you can cut out some other place. So it's just the valuation of the separation when I do the cut. It doesn't tell me where to cut. One more metric which I want you to notice, and this is called modularity. And the idea is the following. Remember that I mentioned to you when we looked at the density that we want to compare, the density within the cluster to the density overall within, in the graph. So modularity suggests slightly different idea. Modularity says the following. Don't compare the density within your cluster to the density in the graph, density of edges. Instead, let's compare the density within the cluster among the nodes you look into with the expected density if the graph was random. What does it mean, a random graph? Well, random graph means that you have all the same nodes. Imagine that you have a graph and it's connected somehow. Then you have a graph, all the same nodes, but then you just randomly connect those nodes with edges, absolutely randomly. So what means randomly? Well, it means you set up a probability that two nodes are connected, and you flip a coin literally. If the probability 50%, you flip a coin. If it is one way, you connect the node, another way you do not connect the node, and so you get completely random graph. So the idea is that if the graph is completely random, it should not have communities, because communities are those regions that are tightly connected, and they're connected by some reason, right? But if you completely randomly do things, there shouldn't be any clusters in there. So the idea is the same as like you take a sand and you kind of spread it around. It should more or less evenly kind of fill the room if you just do it completely randomly. And so if you find some spots where the density of your graph is higher than you expected from random, then there is something kind of fishy going on there, and then this is probably a cluster because the density is above what you would expect in a random setup. Okay, so it's sort of the way to compare things against. And when you don't have anything to compare against, you say, okay, I compare against random. Right? It's a baseline, right? You need the baseline, and you say, okay, I cannot do anything about this. Well, I'll pick just sort of random distribution and look for that. And so that's what's called, and this is that metric called modularity. And the idea is that you compare the number of edges within the cluster compared to how many edges should be, among those nodes if the graph was completely random. And that's how you calculate this. It's number of internal edges in the community divided by the total number of edges. You sum over all communities. And this second term here, it's sum of node degrees within the community. That actually terms, you can prove mathematically that that's what you would expect if the connections in the graph were completely random. Okay? And so what you do is you kind of do this contrasting, the fraction that you have versus what would be if it was completely random. You would say like, okay, why bother? I mean, it's just weird. In fact, this metric actually works pretty well. And it's used in many algorithms, either as a metric we optimize or as a metric we monitor. And when there is a single community, this metric is equal to 0. And then it can go from, -1/2 to 1. Let me show you an example. Come on. I missed that example. Okay. I can't show you because it's not here. I will put the slide in the lecture so you will see, you can look yourself, but there are examples how this metric actually works in practice with pictures. And, it's those examples, in those examples, they're quite convincing that it actually captures this notion of communities. All right. So these are all metrics, right? These are all those sort of metrics that allows us to, evaluate that what we have at hand is a community, but they don't tell us how to find those communities. So next, so the rest of the lecture, we're going to talk about algorithm, how to find those communities. Now, in order to find those communities, we need to have, first of all, some sort of optimization criterion, something we're going to optimize to detect those communities, right? And in this case, it could be the density, like we discussed. It could be the graph cut, right? So those cut values, how many nodes we need to cut out, or it could be this modularity. And there are many more metrics that allows us that you can optimize. And then you need to do something, some sort of optimization method. So you need to start manipulating this graph somehow, and then monitor those metrics. And then when you find something that you think community, you check the metric, right? Now, as I said before, the trouble with just sort of brute forcing yourself through this is that it's really, combinatorial large number you need to go through, combinations, among nodes to actually go through all the possible communities. Even if you think about this for a second, if you take a graph and you think about bipartition, so, taking a graph and splitting it into two parts, right? Just, take a graph, find a way to split it into two parts. How many combinations exist of doing that? Well, you have n nodes. So let's say they're not equal parts, but of course the total sum should stay. So it's n1 plus n2. Well, the number of combinations, how you can do this, is actually n factorial divided by n1 factorial, n2 factorial, which is hell a lot, okay? And that's just bipartitioning, right? Splitting in two. And you don't know, there might be 3 clusters, 4 clusters, 50 clusters. So yeah, you just cannot go through all this. So most of the times, this type of things are solved either by sort of greedy problems, by greedy approximation. And the greedy means, you have your target function that you're optimizing, and you move every step in the sort of downhill. On every step, you kind of choose a direction, or every step you choose, getting sort of better and better value to that function, but it does not guarantee you finding the best overall, right? It's one of those things like you walk on a valley with sort of, I don't know, with hills, and you kind of get the first hill in front of you, you climb it, you reach the top, but then you see that there is a much higher, peak, 1,000 miles, like 1,000 meters away, right? But you're already kind of on this. Well, the problem is when you get there, it's hard to see what's out there. So the point is you don't necessarily find the optimal one. Or there are some, heuristics that somehow work, right? There is no proof that they do work. There is no mathematical proof, but in practice they work, right? And so those are classes of algorithms that you usually kind of use to solve this NP-hard problems. Now, there are usually two approaches. One approach is what's called partitioning. The other approach is agglomeration. Partitioning usually means, you take a graph and start splitting it apart until you cut it like enough number of times to actually have those communities. And we'll see one example of this approach. Another one is agglomeration, when you say, okay, every node in the graph is in his own community, and then start merging them, with each other, the same way as agglomerative clustering works. merging them until they form some sort of communities, then you stop. In both cases, you got this hierarchy, right? Of one way it goes sort of from top down, another way it goes from bottom up, but you get hierarchy, and your actual communities are, you can pick up sort of level in this hierarchy and you get your communities. Do you guys remember agglomerative clustering? Yes? No? Agglomerative clustering? No? Yes? No?
No, I don't remember.
You never done it. Okay. Well, I don't want to go into like sort of details of sort of machine learning data mining applications, but there is a way of finding groups of nodes, how they group, right? And that's called agglomerative clustering, for example. And that's pretty much the same approach here. Anyway, one thing that we would want, of course, that we're expecting is that each community, should be connected, right? That's sort of obvious. So when we do this partitioning, we can actually do what's called multi-way partitioning, which is, okay, here is a graph, and let's just find all the scuts, right? And let's find sort of all those groups right away. This does not work too well. The much better way is what's called recursive partitioning. When you take the graph and you first split it, let's say, in two pieces, and then you take each piece and split it again, and take each piece and split it again, and you keep splitting until you get to the point where, say, the density here is high enough that you call this clusters. So you decompose graph into clusters, right? Or, for example, modularity score is high enough that these are clusters, and then you stop cutting them. I mean, if you continue cutting, of course, you can cut it all the way through to the individual nodes, but that's not the goal. The goal is to find those tightly connected groups. And so the way to do it is to just start splitting on this, on some way, right? Hoping that your algorithm will be smart enough not to, say, cut here, smart enough not to cut here, but it will actually, decide to cut here instead, right? And then decide to cut here and not to cut there. Because if it does that, then, at the end, you will not get any clusters. But if your algorithm is smart and chooses those, red lines, then at some level, you'll get clusters. Okay? All right. So these are all sort of stories around, but how do you actually do this? Bunch of algorithms. I will show you today too, but in the books you can find probably hundreds of algorithms by now, because this is extremely popular topic among the researchers. So algorithm number one is called edge betweenness. Do you remember we talked about betweenness centrality? Can you remind me what betweenness centrality is? Oh, come on. We talked about edges. We talked about degree centrality, right? We talked about closeness centrality, and we talked about betweenness centrality. So what was betweenness centrality? Sort of what's the notion of betweenness centrality?
It kind of tells us about the ability of a node to connect two separate clusters, or two or more separate clusters, not being central in those clusters.
Well, almost. When we talked about betweenness centrality and node, and as centrality for the nodes, we talked about the shortest path that goes through the node, and so node being a bridge between some communities, right? Node being a bridge in between other nodes. That's sort of betweenness centrality. Actually, the word between, right? So this node is between others, right? So that betweenness centrality. And so we just measure, in order to measure it, you calculate the number of shortest path that goes to this node overall. And so that's your metric of betweenness. So you can actually do the same, not only for the node, but for edges, for any edge. And select those edges that are bridges, right? Think about it this way. Think about St. Petersburg, right? Think about traffic on St. Petersburg. When you need to go from one island to another, you need to cross, you go through the bridge, right? And so it's a bridge that has the highest sort of traffic in the city, the highest load. Now, if you look at this picture right now, at the picture at the bottom, you realize that if I start traveling from any node to any other node, right? If it is, you know, if both nodes, you know, lay down here, of course, there is probably a way here. But to get from any node here, any node on this side, to any node here, to any node here, there are only two ways, right? You either go cross this bridge or you cross this bridge, right? This edge. If you want to get from any node there to any node here, well, your ways are you can either go here, here, or here, right? Only three ways. There are multiple ways to get from this node to this node inside the graph, like really, really a lot of ways. But there are only, whenever you try to get from this side to this side, there is either this way you take, this way, or this way at some moment, right? Correct? So if you think about traveling from any node to any other nodes, these edges, this sort of bridges, they play a critical role because most of the shortest paths should go through them. So going back to our definition, it really means that we can measure betweenness centrality for the nodes. And then those nodes that have high betweenness centrality, they will actually correspond to the bridges. Do you see the logic? Okay. And then what we can do is we can just start cutting them out. So you cut out the bridges, you quickly split the graph into pieces. If you want to split St. Petersburg, right, separate people in St. Petersburg, the easiest way to do it is not to barricade streets, but to open bridges, right? This is the smallest number of actions you need to take. And that's what pretty much this algorithm does. It actually finds those edges that has highest betweenness centrality and removes them, okay? And does it iteratively. So what do we see eventually? Well, oops. So this is the algorithm. It's called betweenness centrality or edge betweenness. 2004, pretty old algorithm by now, but it's probably not the most efficient, but it's kind of quite stable. So what it does is it does the following. For every edge on the graph, we compute betweenness centrality. Then you sort them by betweenness centrality. You pick up the edge that has the largest centrality and you remove it. You cut it. All right, and then you repeat this. You know, if you open a bridge, traffic will redistribute. Then you find again the bridge that it is the most loaded, and you cut it also. And then you keep doing it until you cut out, you know, entire cluster. So you keep doing it. Say, you know, you open this bridge. You say this bridge, this bridge, this bridge, this bridge. You know, then you pretty much cut out this. Okay, and the cost of this cut, if I measure it by the cut values, is 1, 2, 3, 4, 5, because I had to cut 5 edges. So that's edge betweenness algorithm. So it's very, very, you know, straightforward in terms of what it does. Now, as I said, it can be done hierarchically. And so, you know, we remove edges and let's say, you know, we split this and, you know, you cut out this then you cut out this, then you can probably start cutting and slice it here, and then maybe here, and then somehow here. And since you do it on every level, you can actually get hierarchy of groups, right? You get the first split of the graph into two groups. Let's say this one, and it splits into two groups, right? There is this group, and then there is this group. And then you take, say, then this group, actually, the way I showed it, sorry, it's this cut, right? So it splits into this orange, red, and green, blue, right? And then, you know, you can actually split this blue and green into two parts. Here's a split, it's this split. And then you keep going. So that's hierarchical partitioning, because you do hierarchical down, and it is edge betweenness because it's based on the betweenness values of the edges. So if I take the same Dockery Club data and run this algorithm, you know, that's the first split it finds. So red belongs to one, you know, the yellow belongs to another. And so in this case, the partitioning by itself happened, you know, along this, well, you know, these edges, right? So that's the edges that has been removed. That's a cut. Now, but as I said, we can actually keep going, right? You can take this red part and keep partitioning. You can take the yellow part and keep partitioning. Keep going and finding sort of those weak spots. And then, you know, in the next level, this is a community it will detect and cut out. So the question is, you know, how far should we go, right? How many communities? Because again, I can go this way for a long time, right? Until I end up with every single node separate. So the way to do this, for example, is to monitor this modularity score. Remember, we talked about the score, and you know, the slide that is missing was supposed to show you that when you have a good partitioning, the modularity score is the largest. And so what you do is we look at modularity score when we have one cluster and it is 0. When we split it into two clusters, this is the value of the score. 3 clusters, 4 clusters, 5 clusters. So modularity metric says that 6 clusters give us the highest value of modularity. And after that, if we keep splitting, modularity is dropping. And so the optimal number of clusters for this graph is, you know, I think it's 6, right? So there's 1, 2, 3, 4, 5, 6, okay? So according to that metric, it's 6 that's optimal. And then, you know, I can actually do this. So according to modularity, the largest value of modularity for this graph is 0, 3, 4, and that's the partitioning into clusters of this graph, for this graph. So the algorithm believes that these are the optimal clusters. You know, you can agree, you can disagree, you can maybe say that this was better or this was better partition. Again, remember, there's a question of partitioning the same way as a question of clustering. The communities are not defined precisely, defined as a group of nodes that are tightly better connected among themselves than with the rest of the graph. Okay, so that's one algorithm. Any questions on this algorithm? All right, you will actually have a chance in a lab to play with the algorithms. And, you know, in many cases, you kind of learn more when you try it on your own, right? But that's sort of what the algorithm does. Okay, and as I said, you know, you can actually see the dendrogram, so which is the the groups, these hierarchical groups, how the algorithm partitions. Okay, very different algorithm. Now we're going to talk about very different algorithm, which is called fast community unfolding. If this edge betweenness was kind of one of the first algorithms, this one is, though it's 10 years old, but in fact, it is still one of the most efficient algorithms out there. It's also pure heuristic algorithm. There is no proof why it should work, right? But it does make reasonable steps, and eventually it converges. Again, there is no proof that what it converges is optimal, but it does a very good job at doing finding the partitioning. So this algorithm, remember, in the edge betweenness, what we did, we calculated those, we found those edges with a high level of betweenness, and we removed them, and then we used modularity to just check on the quality of the solution. Here, we're actually going to try to optimize modularity score by the algorithm. So we try to optimize the score itself by the algorithm, using algorithm. So here's an algorithm, and we're gonna look at it. The idea is that we start by assigning each node to its own community. So it's going to be sort of agglomerating, right? We assign each node to each community, to its own community. And then what we're going to do is the following. We're going to try to merge nodes that are connected into community and see if this is going to improve modularity or not. And if it does, we keep that. And if it does not, we don't do it. So we place a node in the community that maximizes modularity. And we just keep iterating. So let me just show it on the picture, and then it might make more sense. So the idea is every node starts as its own community. And then what you do is you look at this and says, okay, let me take node 1 and node 2 and call them a community. And let's check the modularity score for the graph. If it is improving, then I just keep them as a community. All right, then I take node 3, and I can combine, make a community from node 3 and node 0, or I can make a community from node 3 and node 7, because these are two options here, right? So I check what happens with modularity if I join node 0 and node 3 in one community. And I check what happens with modularity is I join node 3 and node 7 in one community. And I find out that if I connect 3 and 7 in one community, modularity improves more. And so I put them in one community. And you keep doing it with every node, right? And after you're done with this, what happens is you get those groups of nodes assigned to different communities. We don't know how many communities is going to happen, right? This is this iterative process. You just keep going over those nodes, and then you get this. Now, if I go sort of in a different order, if I start with these nodes, for example, I might actually get different distribution of communities. Because remember, the algorithm is greedy. It doesn't find you ultimate truth. It doesn't find you the optimal result. It just says, look, on every step, I will be just maximizing modularity, right? Everything I do, I'll just take that step that maximizes modularity. And in this case, a step is joining nodes into community. And then, so that's the first phase of the algorithm, merging nodes into communities. And then there's a second step where I actually take all the nodes that belong to one community Here they are. And then I aggregate them into supernodes. So all the red nodes become this supernode, all the green nodes become this supernodes, all the blue nodes become this supernode, all the light blue nodes becomes this supernode. And look, there is this in between green and blue, there were 4 ways those 2 groups were connected. So I connect them with the edge and put a weight 4. And there are 4 nodes in this community. And then there is this guy and this guy, and then there is this 4 nodes, etc., etc. So that's all I do. And then you have this new graph, and you pretty much repeat the process that we just did on this new graph. Again, you kind of combine them into communities, and etc., etc., etc. So instead of like an edge between us, we're splitting things. Here, we're merging them into communities. And formally, algorithm looks like that. So again, first phase, every node we assign to its own community. Then we evaluate merging 2 nodes into 1 community, right? And you just connect your node with the other node that increases the modularity of the entire graph. And you just keep doing it. Then when you've gone through all the nodes, you merge them into the supernodes, and then you repeat the process. Now, you would say, why the hell would this work? Well, the answer is, it's a greedy algorithm, and on every step, we're always improving modularity, right? Because every step is based on connecting nodes such a way, or putting nodes in community such a way that it is improving modularity. See, place a node in community, maximizing modularity gain. So every time we're maximizing modularity. So eventually, after we're done with this process, modularity will increase for the graph. Modularity will increase, which means partitioning that we're offering will be better than what we started with. Is it going to be perfect? Who knows? There is no guarantee. But in practice, this works very, very well. And that's why this is heuristic. So there is no proof that it converges to the right thing. But on every step, we do the right thing, right? It's like, you're trying to find your way in a city. You don't have a map, but you kind of, every time you go, you kind of know you need to go north. And so you just keep going, say, north. And you might not find the right place, but you sort of trying to get there, right? You're sort of moving in the right direction every time. Okay. So, and that's just a formal way of presenting this algorithm. So eventually, if I run this algorithm on the fast community unfolding, right? If I run it on a karate network, this is the optimal distribution that it gives. Actually, I do like this kind of clustering better than the one I get from edge betweenness. To me, this is a little bit more, more natural, right? So there's this one cluster, one community. This is the second, right? The third, and the fourth, right? This sort of, to me, this is like a quite natural way to do it. The other algorithm couldn't find it, right? It offered 6 communities. And that's what I was trying to explain to you, that because there is no unique definition, each algorithm optimizes its own thing. So the previous algorithm found the best partitioning according to that algorithm, according to itself, based on the operations that algorithm could do. This one had a different set of operations or different set of action it can do, and it found this partitioning, right? And this partitioning, in fact, has high modularity, so it's actually better. And this algorithm also works on large data sets, and this is an example how it partitions a very large sort of fractal data set. If you notice, it actually does a very good job grouping, similar nodes together, right? So this is called, again, fast community unfolding, or it's also called, it's also called Leuven method, by the name of the university where those guys were who discovered it. So this is a workhorse, and this is the algorithm I usually use if I need to do community detection. Okay.
Can I ask a question?
Yeah. Sure.
But when we initialize this algorithm, we already decide the number of communities that we want to have as an output, or
no.
How do we? Okay.
No, we do not. It actually does this automatically. So what it says, again, remember, at the beginning, the number of communities is the number of nodes we have, right?
Okay.
And so then it slowly merges them, merges until it gets to this level. So, that's, and then you select the number that gives you the highest modularity score. In fact, the algorithm, the way it is implemented, it will return itself to you the optimal number of communities, the optimal number of clusters.
Okay, thank you.
Sure. All right, guys, and this is just this table. It's a summary table. This is actually, I took it from the review, 10 years ago. This is like the review of 2010. By now, there is probably, I don't know, 10 times more algorithms out there. But the key to this table is the following. These are different approaches, different people, and there are different names of the algorithms. And you can look up all those papers and all the references, like full references in this review. But the key here is that, is that side, this column. N is a number of nodes. M is a number of edges. So this really means that, if you take an algorithm of an O notation is a number of operations you need to make it work. And so, for example, an algorithm that is O of, say, n cubed, this algorithm that will not scale because n is a number of nodes. And if you have, 1,000 nodes, which is 10 to the third, you actually need to make order of 10 to the 9th operations to achieve the result, which is 1 billion, right? That's hell of a lot. So typically, algorithm that works in practice is something O of n, right? Or maybe O of n log n. I cannot write it, but something n log n, that will be good. Like, for example, this is, okay, n log squared n, that will work, right? N squared, it's already too much usually for algorithm to be efficient. Now, something like exponential of n, this like in practice will never work, right? This is pretty much only toy algorithm. But something which is O of m, order of magnitude of number of edges, this something that can work pretty well, right? This is also number of edges. And this is the algorithm, by the way, that we're looking at, right? N log squared n is not bad either, right? This is terrible. This might work in practice, and this might work in practice. So that's kind of the thing. When you look at the algorithms, there are on one hand, there are parameters, right? The quality of the clustering that it creates, but on the other hand, the scalability. And when you deal with the real networks, that's extremely important. And seriously speaking, a network with 1,000 nodes, it's very small, right? Think about, again, linguistic networks. If a node is a word, you're just saying, okay, my vocabulary is 1,000 words, right? But that's extremely small vocabulary to have. But then, if it is algorithm n cubed, even on that graph, you cannot just detect clusters with this type of algorithms. So, that's why the complexity, like computational complexity of algorithms are extremely important. All right, okay. Okay, so and that's pretty much it for today. You know, as always, bunch of references, and on the seminar lab session, you'll be able to practice those things. Any questions?
Which fields can you apply this kind of algorithms apart from
Oh,
social?
I mean, there, you know, the partitioning, you know, graph partitioning, it's, I mean, applications are numerous, starting from very simple that were done in like last sort of century, where people, when you try to distribute computations among computers and try to minimize communications, right, and try to find the optimal cuts, to segmentation problems in computer vision, to you know, finding communities for marketing purposes, to, I mean, you name it. It's probably one of the most popular tool of detecting those clusters or groups of nodes, or you know, nodes, or today it's usually called you know, it is unsupervised learning, right? It's unsupervised learning on graphs where without supervision, you automatically detect groups that are very, very well connected, right? And of course, for all kind of social things, you know, you want to find groups of people that know each other or communicate among themselves, between themselves more than others. You know, plenty of applications. If this is interesting, go look into, go look into the review. Okay. All right, guys. Thank you very much. And
Thank you.
yeah, have a good productive evening. Thanks.
Thank you very much.
Goodbye.